Yes, yesterday we looked at some contour representations for certain functions. In particular, we looked at a contour representation for the gamma function, which I claimed was applicable for all values of z explicitly. And if you recall, the way we did this was to start with a representation, the original integral representation, which was valid in the region real z greater than 0. I showed that it was equal to, keeping z in this region, I showed that it was equal to another integral, a contour integral this time, and then I pointed out that the right hand side, the contour integral, actually makes sense for all values of z. So it provides a neat analytic continuation to all values of z of the gamma function. So this was the trick. You find a representation for a function, in the region in which it is applicable you find another representation, that is an identity, but the second representation may be valid in a bigger region, or at least in a region which is partially or fully beyond the original region. But there must be a common region of overlap so that you can call one the analytic continuation of the other. Now let us see what we can do about the beta function, whether we can play a similar trick. In this case, so let us write a representation for the beta function, and recall that we started with a defining representation. This was equal to integral 0 to 1 dt t to the power z minus 1 minus t to the power w minus 1, with the caveat that real z was greater than 0, real w was greater than 0. Okay. So that was our original defining representation, and we need to keep this condition so as not to run into trouble here, and this so that you do not run into trouble at the upper end of integration. In this case, integrating by parts, either of these factors did not work, because if you do that, then while you may improve the convergence in z by taking it to the left to real z greater than minus 1, you will worsen the convergence as far as w is concerned and make it real w greater than 1 and so on. So that method does not work unless you specifically would like to have a representation in some strip or the other. On the other hand, we could exploit the fact that this function, as a function of t in the t plane, has a branch point at t equal to 0 and another branch point at t equal to 1, and we know the phases of these functions on the principal sheet, right. So in the t plane you have a singularity at 0 and a singularity at 1, and since in general z and w are arbitrary complex numbers in this region, it is clear that there is a winding point at t equal to 0 and another winding point at t equal to 1, and that the cut, whatever cut you choose to draw in whichever direction, runs from 0 to infinity from here and 0 to infinity from here, and the discontinuities are given by examining the integrand more carefully. In this case, since it is a product of this form, so to speak, the discontinuity here does not cancel. That would have cancelled if both of them had been square root singularities and not in any other case, but they do not cancel. In general, these cuts will run all the way to infinity. But now if I start by saying that the phase of this integrand is 0 here, just above the real axis, there is definitely a cut here, right. Then imagine what happens, consider what happens if, keeping these conditions, sticking to these conditions, I consider the following contour integral. The phase is 0 out here, and I move along like this, and I go around this once in the negative sense in this fashion, and then I go back in this direction and go around this too in the negative direction sense, again in the negative sense. I come back here and go in the positive sense, I am exaggerating in this figure, and I go around like that in the positive sense. And it is clear what I ought to do is to go around this too in the positive sense. So I come back, remember I started like this, I come back, go around here, and then go around this in the positive sense, come out and join up. And I claim that it joins now, and the function goes back to its original value, because when I went round this contour 1, and here is the symbol for it, so I went round 1 in the negative sense, and then I went round 0 in the negative sense, and then I went round 1 once again in the positive sense, and 0 in the positive sense. So that is the shorthand notation for this contour that I have drawn. And look at what has happened. When I went round in this fashion, this factor here picked up a phase factor e to the minus 2 pi I w, minus because I went round the wrong sense, and it picked up, once I came here down here and went round this in the positive sense, in the negative sense, it picked up a factor e to the minus 2 pi I z. So you started, or starting point started with modulus m, then in the circuit when it went back in this from 1 to 0, it did so with m e to the minus 2 pi I w, and that function now you went round the point 0 in the wrong direction sense, so it picked up an extra phase e to the minus 2 pi I w e to the minus 2 pi I z, and then I undid the two things. So I got rid of this, so it went to m e to the minus 2 pi I z, and then it went back to m in this fashion, because it got multiplied by e to the plus 2 pi I w and got rid of this factor, and then it got multiplied by e to the 2 pi I plus 2 pi I z, got rid of this factor, you are back to m. So you are guaranteed that this weird looking contour is a closed contour. Every one of these segments, I have exaggerated this, every one of these segments is running from 0 to 1, just above, just below the cut, etc., etc. I do not need to draw the cuts because it is quite a complicated structure. So I am getting onto all kinds of sheets of this function, but you are guaranteed that this contour C is a closed contour in this case. And now the point is, what about the contributions from all these small circles? Take a typical contribution here round z, this thing here for instance, then this is going to give you an epsilon, because t is epsilon e to the I theta. This is going to give you an epsilon to the power z minus 1, which is an epsilon to the z, and this does not do anything, you can set t equal to 0 in this, and since real z is greater than 0, epsilon to the power z tends to 0 as epsilon tends to 0. So this contribution, these contributions are guaranteed to be 0 in this region. But once you have written it in this form, then of course you are away from the point 0 and 1, the contour never passes through either 0 or 1 at all, and therefore no matter what you do with z and w, it is not going to change the convergence of the integral. And each time you multiply, you are going to pick up a phase factor, and I would like to ask what is the integral over m itself equal to, that is what this beta was. So it turns out that this beta is also equal to 1 over, exactly as we done earlier, 1 minus e to the 2 pi I z, 1 minus e to the 2 pi I w, an integral over C, it is a closed contour, dt t to the power z minus 1 minus t minus 1, and that is valid for all z and w. Now all the singularities of this function are going to show up from the zeros of this denominator here, and when there is no singularity at all, even though this might vanish, it is going to be cancelled by a 0 in the numerator. So once again, when you go to the left of this region, you are going to encounter singularities, poles, but you can extract what the residue at the pole is from this expression here in principle. Okay. But of course we also know that this quantity beta of this is equal to gamma of z, gamma of w over gamma of z plus w. So you could extract the singularity structure of this beta function also from this representation, and that is valid for all z, every z. So wherever you are in z and w, that formula is always true as an identity, and therefore you can extract all analytic properties of this function from there or from this integral here. This sort of contour, this kind of thing is called a Pochhammer contour. and the notation is you have various branch points, you simply is telling me in what direction are you going around the branch point and in what order. Okay. So that is a very compact way of writing this contour here. So the moment you write that, I immediately know that the contour is running from 0 to 1, between 0 and 1, back and forth with this sign convention. Of course, it is not a unique way of writing it, there are other contours which are equivalent to this. What is interesting is that if you actually wrote this contour out on the Riemann sphere, then it looks extremely symmetric, because on the Riemann sphere, remember there is also a branch point at infinity here in this function. So on the Riemann sphere, what happens is that, just for sake of representation, we know that infinity is sitting there, 0 is sitting here, and 1 is sitting on the equator out here, but for the moment let me write them as 3 points here, and then this contour looks like a nice trefoil knot, looks something like that. You can slip things around, distort them around and so on till it starts looking like this, and you are guaranteed that is a closed contour once again. So this method of using contour integrals to provide representations for functions is an extremely useful one, and all kinds of analytic functions can be represented in this fashion. Generally they provide you with representations valid in a huge region, if not the whole plane. Let us look at another function which we have looked at a little bit earlier, namely the zeta function, and ask what happens there. Can I find a representation? This is the Riemann zeta function, and I recall some properties which we had deduced a little earlier. Recall that we defined zeta of z to be summation n equal to 1 to infinity 1 over n to the power z. That was this defining representation, and this was valid as long as the real part of z was greater than 1. If it is 1, it is logarithmically divergent, as you can see. So we have a representation that is valid in the complex z plane to the right of the point 1, and here is 0. Now as we know from our experience with power series, on the boundary of the region of convergence you expect one or more singularities of this function, provided it can be analytically continued. In this case it will turn out that there is a simple pole at z equal to 1, and it is analytic everywhere else, and therefore you can analytically continue it down here. And now the trick is to find out what is this representation, what representation will show me explicitly that there is a pole at z equal to 1 with residue 1 as it happens, and to the left of it the function is well behaved once again. Well, the trick is to start not with zeta of z, but to start with gamma of z times zeta of z, and write representations for each of these. So this is summation n equal to 1 to infinity 1 over n to the power z, an integral from 0 to infinity d, let me call it some other symbol, du u to the power z minus 1 e to the power minus u. This was the defining representation for the gamma function, provided real z was greater than 0, but this series converges only if real z is greater than 1. So this whole formula is valid only if real z is greater than 1. And in that region the series converges absolutely, the integral converges absolutely, and so on. You can interchange the order of integration, summation and so on. So let us set put u equal to n times t. So this thing becomes equal to summation n equal to 1 to infinity 1 over n to the power z, and then integral 0 to infinity. There is an n du, and then an n to the power z minus 1, t to the power z minus 1, e to the minus nt, and the various factors of n to the power z cancels out dt. This is n dt times that, and the factors of n cancel out completely, and then I can interchange the order of summation and integration. So this becomes equal to an integration from 0 to infinity dt t to the power z minus 1, and this is a geometric series e to the minus nt starting from n equal to 1. So the answer is e to the minus t over 1 minus e to the minus t, because e to the minus t is less than 1, and I multiply through by e to the minus t, and it just becomes this divided by e to the t minus 1. So that is an integral representation, and we still need to keep real z greater than 0, because there is a problem here, this guy. In fact, we need to keep real z greater than 1 as it should be, because we have not done anything. This is true. Why is this necessary once I write that representation? Because look at what happens to the denominator. This is e to the t minus 1, so the 1 cancels out and the leading term is t in the denominator. There is already a power minus 1 here, so there is a t squared in the denominator. So this power had at least better be at least 1, greater than 1, otherwise you have a singularity. So it is still true that real z greater than 1, that is still true, that condition is still needed. But now we can play the trick that we played earlier with regard to that integral. To get rid of the singularity at 0, I convert it to a contour integral. So once again I resort to contour integration by saying I look at the t plane, and this factor here t to the power z minus 1 has a branch point at t equal to 0 and t equal to infinity. I draw a cut between the two in this fashion. The phase of the function is 0 here, it is e to the 2 pi I z here. So I consider once again this hairpin contour. Going below the cut from infinity to 0, going around 0 in the negative sense, and then going off to infinity once again just above the cut. Okay. So on this contour, this portion of the contour, this function is modulus multiplied by e to the 2 pi I z, and out here the modulus is the argument is 0. So this can also be written as equal to an integral over this contour. It is not a closed contour, dt t to the z minus 1 over e to the t minus 1, and there has got to be a 1 over 1 minus e to the 2 pi I z. The 1 because this portion is just the original integral, and the minus because I am coming in from infinity with a phase factor e to the 2 pi I z. So it is exactly as it was before. So this tells us that we have a representation for this zeta function. This is equal to 1 over gamma of z 1 minus e to the 2 pi I z contour integral dt t to the power z minus 1 over e to the t minus 1. Okay. And now you see this contour no longer touches 0 at all. So in principle it is valid for all values of z. This thing here is an entire function of z, and all the singularities of this zeta such as they are must arise from this factor here. The gamma function has singularities, e to the 2 pi I z could be equal to 1 for various values of z, and you could have singularities. Now we can simplify this a little bit by using the following reflection formula. Recall we used the beta function to derive this reflection formula, which said gamma of z, gamma of 1 minus z was equal to pi over sine pi z. That was a reflection formula for the gamma function, if you recall, and let me use that. So we have, I am going to pull out an e to the minus I pi z, put it up on top, that gives me e to the I pi z plus e to the I pi z minus z. I multiply and divide by e to the minus I pi z. So this becomes minus 2i sine pi z. So this is equal to minus 2i. So let me write this as I over 2 gamma of z sine pi z. And I will use gamma of z, gamma of sine times sine pi z is pi over gamma 1 minus z. So let us write this as 2 pi and a gamma of 1 minus z times this. Okay. I mean I am doing this so that I have two sources of singularities, one is a gamma function, the other is sine pi z. I have combined them so that I can keep track of it. There is just one source of singularity here. Now where is the gamma function singular? Whenever its argument is 0, minus 1, minus 2, etc., which means that this thing here gives you a singularity at z equal to 1 as we suspected at z equal to 1. There is some kind of pole, this is an entire function, and then possibly at z equal to 2, 3 and so on. But we know that is not true at z equal to 2, 3 and so on. Zeta of 2 is fine, it is pi squared over 6. Zeta of 4 is pi 4 over 90 and so on, but we have to see what goes on for positive values of positive integer values of z, 2, 3, 4 and so on. On the other hand, what happens near z equal to 1? Well, this thing here as z tends to 1 goes to 0, t to the 0 which is 1, so that is harmless. On the other hand, this factor has a 1 over t, and you know that integral dt over t is 2 pi I, except we are going around in the wrong sense, so it is a minus 2 pi I. So this whole thing goes, zeta of z goes as z tends to 1 to the following, it goes to I. In all harmless factors you could put z equal to 1 including this factor, but you got to keep this. Now what does gamma of anything do, gamma of w do near w equal to 0? It goes like 1 over w, residue being 1. So this thing goes like I e to the minus I pi over 2 pi, and then this is 1 over 1 minus z. So that is equal to minus 1 over z minus 1 in this fashion, and then an integral dt, z goes to 1, that is harmless, over e to the t minus 1 over this contour. But what is that equal to? There is no branch point anymore, because the moment z becomes an integer, the branch point disappears and it either becomes a harmless monomial or a pole at that point. In this case the numerator just disappeared, but you still have a singularity. You still have a singularity because this quantity here e to the t minus 1, the 1 cancels and then the next term is t plus t squared over 2 factorial plus dot dot dot, which you could write as t into 1 plus t squared over 2 factorial, t over 2 factorial plus dot 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 in this fashion. So you could write this whole thing as t here down here, and then you have 1 plus t over 2 plus dot 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 to the power minus 1. So this thing tells you clearly that this integrand has a simple pole at t equal to 0 in the t plane right here. And moreover, this contour goes, as in this case, to just a simple pole. This portion of the integral cancels out against that, this goes away and you are left with just this, that is minus 2 pi I times the residue. And remember dt over t around the unit circle is plus or minus 2 pi I depending on whether you traverse it in the clockwise, anti-clockwise or clockwise sense. So that gives you another minus sign and a 2 pi I, and that of course tells you that this is equal to, if there is any justice in the world, you are going to have these minus signs cancel and then you have an I over 2 pi 1 over z minus 1, and then that was a minus 2 pi I plus the regular part. due to all the other terms that are there, due to all the other terms that come even from this, as well as the gamma function. All of them have regular parts at z equal to 1, but we are extracting only the singular part here. And when you do that, since I know this has a simple pole at z equal to 1, I put z equal to 1 everywhere else and keep just the 1 over z minus 1 term here to find the residue out here. And this is equal to 1 over z minus 1 plus regular part. So we have now come to the conclusion that the zeta function has a simple pole at z equal to 1 with residue 1. Because this coefficient is 1. So we know that this representation, whatever the original summation representation was, is actually valid even to the left, I mean can be continued analytically to the left of real z equal to 1, but at z equal to 1 there is a simple pole and no other singularity at all. What about positive integer values of z like 2, 3, 4 and so on? They too seem to be giving us a problem, because the moment you have 2 or 3 or 4 out here in this representation, this gives you a pole at all these points. So if I put z equal to n, so as z goes to n equal to 2, 3, 4 etc., these integers, this function here is going to have a negative integer argument. At z equal to 1 the argument was 0, it gave you a pole. Otherwise if you put z equal to n, you are going to get gamma of 1 minus n, that has got a pole. So the pole term is going to have I times, I want to extract what happens, so you have e to the I pi times z, so e to the I pi times n minus 1 is going to sit there, so that is minus 1 to the n minus 1. And then this gamma function, well that has got a singularity, so this looks like minus 1 to the n over z minus n, and then there is an n minus 1 factorial, minus 1 to the power n minus 1, because that is what the negative integer is, minus of n minus 1, and there is a 2 pi also sitting here. And then look at what happens to the integral. This integral here will vanish, because in this case the moment I put t equal to 2, 3, z equal to 2, 3 etc., etc., you have a power starting here at least at t, maybe t squared, t cubed and so on, and this guy here gives you a t in the denominator, so there is no singularity at all and the whole thing vanishes. So the moment I put t equal to n or whatever, that term vanishes, the integral vanishes identically. So I have to go to the next term, and the next term is going to be proportional to z minus n, because that is what this whole integral is going to be. So I am expanding this integral as integral c dt t to the power n minus 1 over e to the t minus 1, and that I argued was 0, plus the next term. So the next term was z minus n times whatever is the derivative of this function. And what is the derivative going to be? Well, let us write t to the power z minus 1 as e to the power z minus 1 log t. I differentiate it now with respect to z. I differentiate it with respect to z, and it gives you again the derivative of this is going to give me an integral, contour integral dt t to the power n minus 1. If I differentiate this, I pull out a log t in the denominator. So there is a log t over e to the t minus 1 times z minus n, which cancels out. So I have an I over 2 pi, this fellow gives me 1, n minus 1 factorial, and then I have to do this integral. But yesterday I showed you how you could do an integral from 0 to infinity by putting in a log and then going over to the hairpin contour. Now we want to do that in reverse here. So it is clear that this Pochhammer contour above the cut this log t is log modulus t, but below the cut it is log modulus t plus 2 pi I, and it comes with a minus sign because you are going from infinity to 0. So I could write this as an integral from 0 to infinity dt t to the n minus 1 times minus 2 pi I over e to the t minus 1, and then the 2 pi and the I cancels with minus 2 pi I, and you are left with 1 over n minus 1 factorial 0 to infinity dt t to the n minus 1 over e to the t minus 1. So we assert that zeta of z, zeta of n equal to 1 over n minus 1 factorial integral 0 to infinity dt t to the power n minus 1 over e to the t minus 1, n equal to 2, 3, dot dot, etc. That is a well behaved integral, there is no problem at the origin due to this factor, and at infinity this gives you a convergence e to the minus t. And in fact if you go back and look at the original representation for the zeta function, you could put this in immediately, because recall that we started by saying gamma of z, zeta of z was a certain integral. Put z equal to n in that formula and use the fact that gamma of z is n minus 1 factorial, bring it to the right hand side, that will give you this factor, and the rest is precisely this. So this just checks out that what we have done is consistent. This is in fact the starting representation. Okay. So we know that zeta of n is well behaved, and zeta of z in fact is well behaved for real z greater than 1, and that this integral representation does not give you any spurious poles at n equal to 2, 3, etc. What happens for negative values of integer values of n, including 0? That is interesting. Let us see what happens to this function when you have n equal to 0, minus 1, minus 2, and so on. I already pointed out that zeta of 2 was pi squared over 6, zeta of 4 was pi 4 over 90, and so on. But I also said at that time that there is no simple formula for zeta of 3, zeta of 5, and so on. But there is always this formula, the one that we wrote down now, 1 over n minus 1 factorial, this integral with an n there. That is all, we could always do that numerically, no problem about it. What about negative integer values of z of z? Well, I have asserted that there is a singularity at z equal to 1 and there is nothing else. It is actually well defined everywhere else. So in particular I would like to know what happens at 0, what happens at minus 1, minus 2, and so on. Okay. For this all we have to do is to substitute the value of z inside there and look at what is going to happen. We need a little preliminary for that, and the preliminary that we need is the following. The function t over e to the power t minus 1, consider this function here. Okay. This can be expanded in a power series in t, because near t equal to 0 this thing goes like t in the denominator, and that cancels against this, so it gives you 1 as a leading term, and then the next term is of order t, t squared, etc. So if you expand this in a power series, this by definition is written as n equal to 0 to infinity t to the n, and then you put an n factorial here because there is an e to the t here, and I will explain what the role this plays, and it is multiplied by something called bn, and these are the so called Bernoulli numbers. And it is a simple matter to write the power series out here and then try to track down the coefficients of t to the power n. Gets a little tedious after some time, but there is nothing in principle to stop you from doing this, and b0 equal to 1. That is obvious, because if you set t going to 0, it is clear this denominator and numerator both cancel and give you 1. b1 equal to minus a half. That is also obvious because the next term here is going to be t squared over 2 factorial, take out a factor of t, you get a 1 over 2 with a t, and then when you take it upstairs because you are raising it to power minus 1, it is going to give you a minus half. Okay. Then the next term b2 turns out to be 1/6, b4 turns out to be minus 1 over 30, b6 turns out to be 1 over 42 and so on, all odd bn equal to 0, n greater than equal to 3. So that is the peculiarity of this function. It does not have any odd powers except the leading term proportional to t. So this thing goes like 1 minus half t plus 1/6 t squared, and then everything else is powers, even powers of t alone when you make an expansion. Okay. So it looks like all the b's are decreasing as you go to larger values of n, all the Bernoulli numbers appear to be decreasing, and then there is a 1 over n factorial here. So does not it look as if this whole series is going to have a radius of convergence that is infinite, because there is a 1 over n factorial and then it is multiplied by coefficients. If you did not have the bn's, then this is just e to the power t, which as you know has an infinite radius of convergence, and now you are multiplying it by b's which are sort of decreasing. So what would you expect is the radius of convergence? Infinity is what you would expect. But what happens on the left hand side? Is this an entire function? I agree the pole at t equal to 0 gets cancelled out, it is a removable singularity, but are there any other singularities? Well, if they did exist, where would they be, at what points? When the denominator vanishes. And when does the denominator vanish? Pardon me?
0, t equal to 0.
At t equal to 0. But think complex. When is e to the t equal to 1? When t is 2 pi ni. At t equal to 0 you have a removable singularity because of the numerator, but certainly this function has poles at t equal to 2 pi ni where n is any non-zero integer. So this left hand side as a function of t definitely has poles at all the 2 pi ni. So it has a pole at 2 pi I, 4 pi I, 3 pi I and so on, minus 2 pi I, 2 pi I and so on. And you are making a power series expansion about this point. So what will be the radius of convergence of this? 2 pi. Yeah, it is 2 pi. So this series is guaranteed to converge only inside a circle of radius 2 pi. What does that imply about the bn's, by the way? What must be happening as n increases? They should start increasing at an alarming rate. So it looks like first few of them are small, but eventually they take over and they have to kill this, the effect of this. So they indeed increase quite rapidly as you go on. So this shows you that even if you define such a thing, you can say a lot about this because we have a representation for the function explicitly out here. Now look at what happens here. I am going to find what zeta of 0 is. So zeta of 0 is equal to, there is an I over 2 pi that I can't get over, and then e to the 0, gamma of 1 is 1, and then an integral over this contour dt over t e to the t minus 1. But let me write this as t squared and then it is t over e to the t minus 1. And it looks very much like there is a pole. This definitely looks like there is a pole of some kind, because you can see that this function here, when I have set this equal to 0, there is already a 1 over t here and this guy also is a t. So this goes like a t, 1 over t squared, and then there are terms of order 1 over t, order t to the 0 and so on. So this thing here, instead of that, let me write this as b0 plus b1t plus b2t squared over 2 factorial plus etc. And what is the contour now? Because there is no branch point, it is just a circle round, a small circle round 0 in the negative sense. So the contour becomes this around the origin. But we know that dt over t squared, the contour integral is 0. The only thing that is non-zero is dt over t. dt times any positive power of t or 0 power of t is 0, negative power is all 0 except 1 over t. So this answer is equal to I over 2 pi minus 2 pi I times b1. Which is equal to minus a half. Okay. So zeta of 0 is minus a half, exact value. Well defined numerical value is minus a half. Now if you put z equal to 0 in the defining representation, so if you had n equal to 1 to infinity 1 over n to the power z and I put z equal to 0 here, I end up with the series goes 1 plus 1 plus 1 all the way to infinity. So the series makes no sense, it is not a good representation anymore, it is not valid in this region, but the analytic continuation exists and gives you a perfectly well defined value which is minus a half. What happens if you put zeta equal to minus 1? Well, exactly the same thing is going to happen. If you put a minus 1 here, there is already t squared in the denominator. I put an extra t here, so there is a t cubed. So let us put zeta of minus 1 is this whole thing. And what is that equal to? Well, you can read off what is going to happen. The term that is going to contribute is this alone. That is the only term that is going to contribute, right? And what does that give you? It gives you this term here b2 and then there is a minus sign because you are doing this in the counterclockwise sense and you end up with 1/12 as the answer. Should be minus 1/12, I am not sure where I am missing a minus sign. Zeta of 1 is minus a half, zeta of minus 1 is 1/12, yeah that is correct, it is 1/12. And this was the famous result that Ramanujan wrote in his second letter to Hardy in 1913 when he wrote to him saying that he had a theory of divergent series. Ramanujan did not know about analytic continuation, he did not use complex analysis, he had his own, as Hardy later on put it, tenuous means of deducing these results, but they were correct results. And this letter he wrote saying that according to his theory of divergent series, this series 1 plus half n equal to minus 1, so it is 1 plus 2 plus 3 plus all the way to infinity. He said this is 1/12. So what he deduced was the value of zeta of minus 1, okay, by his own means, by his own methods. And then he writes there saying that if I were to tell you that the sum of the series 1 plus 2 plus 3 all the way to infinity is 1/12, you will at once point out to me the way to the lunatic asylum, but that is what my theory gives and so on. Today we know that what he had done was to find the correct analytic continuation of the zeta function for this value. What happens if if n is minus 2 or minus 4 and so on? So let us look at the zeta function, zeta of minus 2n, and again all we have to do is to substitute this formula here. this is equal to I over 2 pi e to the, and this is minus 2n, so that just gives you a 1, and this gives you a gamma of 2n plus 1, which is 2n factorial over 2 pi out here, and then a contour integral dt over, and this is minus 2n, so you have 2n, and then I add a 2 here, and then I put in b naught plus b1t plus b2t squared over 2 factorial plus b4 t4 over 4 factorial plus dot 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 all the way, and there are no odd powers at all. And if n is equal to 1, 2, 3 etc., when n is 1, then we are looking for zeta of minus 2 out there, then this is t to the 4, and you need a t cubed there to give you a non-zero contribution. Okay. So what is the value of zeta of 2n? 0, it vanishes, so this is equal to 0. Yeah. So the zeta function has zeros at all the even negative integers. These are called the trivial zeros of the zeta function. So what you found a trivial zero, I mean they are easy to find, so they are trivial. And of course you know the famous hypothesis of Riemann says that all the non-trivial zeros of this function, so there are zeros, trivial zeros at minus 2, minus 4, minus 6 and so on, that follows directly from this expression here. But in addition there is an infinite number of zeros on the line, this is 1. So on the line with real part half, Riemann's hypothesis was that there is an infinite number of zeros on this line, and that all the non-trivial zeros lie on this line. That was the famous hypothesis. Now what we have been able to show numerically is that the first 13 or 14 billion zeros all lie on this. By the way, the zeta function is a real analytic function, it is real for real values of the argument. So that implies that if you had a 0 here, you would have a 0 here too, okay, by reflection. Okay. And then all the zeros that lie on this would be non-trivial zeros, and there is a certain distribution of these zeros which is of great interest in many problems, many unexpected problems. But to date what has been shown, as far as I know, is that all non-trivial zeros lie on this almost surely in the rigorous probabilistic sense, namely with probability 1 they lie on it, but this is not the same as showing that all zeros which are non-trivial lie on it. It is also known that an infinite number of zeros lie on this. What has not been proven completely is that there are no other zeros other than those here and on this line, that has not been proven, but it is continually, the number of zeros is continuously increasing, and there is a certain interesting level, interesting spacing or distribution of these zeros which is connected to the distribution of primes, which is connected to the energy eigenvalues of quantum mechanical systems whose classical counterparts are chaotic. It is connected to the eigenvalue spectrum or distribution of eigenvalues of certain classes of random matrices, energy levels of complex nuclei and so on. So there is a very large number of unexpected connections with the zeros of the Riemann function, and this hypothesis is the most important problem, unsolved problem in mathematics, because if it is established then a huge number of other theorems follow immediately. It is a crucial thing, you might want to try, but it is worth understanding this problem completely. So that is for zeta of minus 2n. It is also possible to find out what zeta of an odd negative integer is, minus 1, minus 3 and so on. I leave that to you as an exercise. Minus 1 we already did, because all you have to do is to put a 1 here and then make this a 2n plus 1 instead of 2n, and then find out what the appropriate coefficient is. So I believe 8 of 2n minus 1 is, I think I am not sure about this, there is a minus b2n over 2n or something like that, because there is going to be a 2n plus 1 factorial here, and there is going to be 2n factorial here, or 2n minus 1 here and 2n there, and there is going to give you a 2n out here. Okay. but in any case those are easy to write down in terms of the Bernoulli numbers. So much for the zeta function. There are many other properties of this. The whole of analytic number theory is based on the very intricate properties of the zeta function, for which I have written down here a sum as a representation, but there is also a very interesting representation due to Euler as an infinite product which involves only the prime numbers. So there is a very close connection between the zeta function and the distribution of primes, and that is how, as you know, the primes are the building blocks of all arithmetic, and this is how the connection of analytic number theory, intimate connection with the zeta function, arises. Now I would like to turn next to some other functions like the Legendre functions, but we will do that next time since we have run out of time, and I will talk about an integral representation for the Legendre function, and then perhaps a few other special functions as well. Since you are already familiar with the real representations, the representations of these functions as solutions of differential equations, power series and so on, it will make sense to be able to write them down in terms of contour representations, and we will do that next time.